Okay, welcome everybody to another MCRN Colloquium. Today we're lucky to be joined by Dr. Masato Hara, who got his PhD just 2 months ago from Kyoto University and is now at Hitsubashi University. Today he'll be talking to us a bit about reservoir computing, and very much looking forward to hear that. It's a very interesting topic. And with that, please take it away.
Yeah, thank you very much for introduction, and I'm very happy to participate in such a great colloquium. Yes, let's start. Today's talk is a mathematical mechanism of reservoir computing for dynamical systems, and this is a joint work with Professor Hiroshi Kokubu from Kyoto University, and he is my supervisor on PhD days. And the talk is based on the papers now submitted, and unfortunately, this is not on archive or not another website. However, after this paper is accepted, I will try to upload it on archive or any other way. Okay, anyway, maybe, by the way, maybe many of you don't know about the Hitotsubashi University, so I try to introduce very shortly on Hitotsubashi University. This is main campus of Hitotsubashi University. This is located in Tokyo. And maybe many of you don't know about Hitotsubashi University, but this is very natural because Hitotsubashi University is a historic but a university for social science. However, Hitotsubashi University includes some experts in dynamical systems like Yoshitaka Saiki. He is a collaborator of Professor Jim York or Professor Evelyn Sander. And Katsutoshi Shinohara, he is a collaborator with Professor Oshinga et al. So, but I don't know why. However, by the way, I'm now in Hitotsubashi University and doing work on dynamical systems. Okay, and I shortly try to introduce the relationship between MCRN and reservoir computing, and I obtained PhD degree with a study on reservoir computing under Professor Kokubu, and this talk is based on the work in my PhD days. And maybe some of you knows reservoir computer can be used for analysis on time series including climate dynamics, like ocean or typhoon. And I started a new project this year related to typhoon dynamics. And so I'm very newcomer for climate dynamics, but I have to understand something on typhoon dynamics. And I don't know I will use reservoir computer for typhoon dynamics or not, but I'm very interested in, and I'm very glad to give a talk in this colloquium. Okay, today's talk is has two parts. The first part is main part. This is introduction or abstract of our study, but the most important message is contained this main part. And the latter half is a technical part. This is here I try to tell the outline of the proof to main theorem main theorem presented in main part. But this part is a little technical, so maybe I omit some of these parts. So I apologize it in advance. And finally, shortly, I will try to conclude this talk and going ahead to the question. Okay, then let's start the main part. Firstly, reservoir computing is a kind of machine learning method based on recurrent neural networks. Note that the deep learning method or something, another famous method is basically a neural network, so-called hierarchical neural network. But reservoir computing is very different. Essentially different from the viewpoint of the structure of the neural network, and the concrete way to formulate the recurrent neural network or reservoir computing is given in the slide after this. But before introducing the reservoir computing, I first try to give the aim of our research. That is time series prediction. The setting is like that. For a given time series, this is generated by a dynamical system on a manifold M. But we suppose this F is not known a priori. And phi, this is a map from M to Rm. Actually, this should be embedding of the manifold M to the high-dimensional Euclidean space. And this can be seen as an observation function from a manifold to Euclidean space. So in this setting, we can write xn plus 1. This is a point on M. It is generated by fxn, and the time series can be taken by phi xn. And what we want to do is to understand the dynamics of F behind the data. The meaning is that, for example, in the task of prediction of the logistic map case, this is a result of the logistic map prediction by using reservoir computer. As you see this, the blue solid line is a target dynamics, and orange dotted line is a prediction dynamics. As you see, the long time prediction is not succeeded in this graph, but as you know, long-term prediction itself is impossible essentially because of the chaoticity. However, the dynamics of F can be reproduced by reservoir computing in the sense of the right figure. This is a plot of xn comma xt comma xt plus 1. So this light graph shows that the dynamics of dynamics of prediction is mimicking the dynamics of the logistic map F. That is a quadratic function like this form. So what we want to do is such a thing. And another remark is that because the dynamics of F can be reproduced by a reservoir computer, so the attractor of F can also be reconstructed like this. This plot is different from the plot of this logistic map xt plus y plot, but this is because this is of course the Enon attractor for the Enon map fxy. So the x coordinate and y coordinate, and this orange dot is prediction dynamics, and blue dot is target dynamics. And as you see this figure, the dynamics of N. The dynamics of N and attractor of N is very goodly reproduced by reservoir computer. So what we want to do is why such a thing can be why such a thing occurred by using reservoir computing. Understand why such a thing can be done by reservoir computing is our work. So let's move on to the formulation of the reservoir computer. We investigate reservoir computing with eco-state network. In fact, there are some many arranged version of reservoir computing now, but eco-state network is the original version of reservoir computing. by using recurrent neural network. Okay. In this talk, we fix A, C, and B as a matrix, and omega is a concatenation of this matrices A, C, and B. And we put Y as Rn, and tau bar is the component-wise tau. So with tau is a map from R to R. This is so-called activation function in the area of machine learning theory. And but generally, tau can be taken arbitrarily. However, we use tau equals to tangent hyperbolic in this talk because of the tradition of the reservoir computing theory. Yeah, but basically tau is tau can be chosen arbitrarily. And under this setting, we define the reservoir map F omega. This is a map from M. M is a manifold, and Y is Rn. And F omega is a map from M times Y to Y by this form. For short, F omega can be written as tau omega phi x1. And this means tau A Rn plus C phi xn plus B. If you know reservoir computer well, you can find that A is a kind of, A is so-called internal connection, and C is so-called input matrix, and B is so-called bias. Okay, but in this talk, we concatenate this A, C, and B, and we think that omega is a randomly chosen and fixed parameter of the reservoir map. And the reservoir algorithm is very simple in the world of neural network. So this algorithm can be written in this only one slide. And the algorithm is contains 3 steps. And first step is so-called listening phase, and second step is learning phase, and third step is predicting phase. In the listening phase, we do update the internal state Rn. We call sometimes reservoir state by using reservoir computer with this formula. And recall that we think that the time series xi n is time series xi n is observation of time series xn, and xn is driven by the dynamical system, unknown dynamical system here. Okay, and in step 2, by using Rn's given in step 1, determine an output matrix double to minimize the error between WRN and XN. So formally, we can write such a form. What we want to do in this step 2 is, excuse me, what we want to do in step 2 is to make an error between WRN and XN. So in step 3, a predicting phase, okay, in step 3, predicting phase, we do such a thing. So put F2 the omega double from Y to Y, defined by this form. So the difference between step 1 and step 3 is in step 1, one uses the xn in the first coordinate of this map F omega. But in step 3, we use double Rn different from xn. The reason why use double Rn in step 3 is that in step 2, we fix this double as make sure to double Rn and x close. So we think to put double Rn rather than Xn. But by putting double Rn rather than Xn, this F omega double can reproduce the parentheses Xn after the learning time T. So after T, okay? Okay, so this is Reservoir algorithm. So now we can state the main theorem in formal form, but before that, before stating that, we have to give a definition of that is semi-conjugacy in the weak sense. This is used just in this slide, just in this work. So generally, if F and Z is a dynamical system on X and Y, respectively, and we say that Z is topological semi-conjugate to F in the weak sense, if there exists H, just continuous that diagram of this commute. The difference between topological semi-conjugacy or topological conjugacy is that the assumption for H is very mild or weak in the the semi-conjugacy in the weak sense definition. So if there exists H of homeomorphism, then we call the system F and Z is topologically conjugate. And this H is continuous and onto, we call this F and this Z is topologically semi-conjugate. But we make mild the assumption for H to just continuous. And in this sense, we call this situation a semi-conjugacy in the weak sense. Under this setting, our main theorem can be stated like that. For a reservoir F omega that satisfies some reasonable assumption, and for a good enough dynamics F, the autonomous reservoir that is defined in step 3 in the form of this, which learned F and step 1 becomes semi-conjugate to F in the weak sense in many cases. So this is the informal statement of main theorem. And to conclude this main part, I want to give an outline of the proof. This is we call ideal reservoir strategy. So what we have to prove is this. So for good F omega and F, there exists some capital H from gamma double to lambda. Here, gamma and lambda is attractor of F tilde omega double and F respectively, such that the left diagram commutes. But to say this directly is hard. I think maybe impossible. So I consider the ideal reservoir F tilde omega gamma on gamma gamma to gamma gamma. For precisely speaking, in step 1, this step 1 is related to the step 1 of the algorithm. So this listening phase. There exists gamma, map gamma from gamma gamma to lambda. This is so-called ideal output, where gamma gamma is attractor of F tilde omega gamma. This is defined by F omega gamma R R. So note that we call this ideal autonomous reservoir, but note that this definition of F tilde omega gamma is clearly correspondent to the definition of the autonomous reservoir F tilde omega double. The difference of the autonomous reservoir F tilde omega double and the ideal autonomous reservoir F tilde gamma double is just here is double or R. Okay, so and in step 1, we show that this ideal autonomous reservoir F tilde omega gamma makes the lower part of the left diagram commutes. And in step 2, we show that double and phi is after gamma is very close in the sense of caesar function. Here, note that gamma is a function from the space of from y, so very larger Euclidean space to the abstract manifold M, and phi is a map from abstract manifold M to Rm. Here, small m is very smaller than capital M. Okay, and W is a linear map from R capital N to R small m. Okay, so the basic message of this nearity is that the output double obtained by this learning phase by using this, that is so-called linear regulation, is mimicked by gamma. This is ideal output. Okay, hence the f to the omega double and f to the omega gamma also very close in the sense of C0. This is the step 2 of the proof. And the final step to conclude the proof of this main theorem is that there exists there exists small h from gamma double to gamma gamma. In fact, this h can be very close to identity in the sense of the map from y to y, or r capital N to r capital N. And the h make the upper part of the left diagonal commute. However, unfortunately, this h in step 3 can be just a continuous map, not C1 Diffeo, or excuse me, not C1 Diffeo or Homeo or continuous and onto. So the map H defined by gamma after H, yes, gamma after H is the is just she's a map or a continuous map. So we only say in this strategy is that the conjugacy in the sense of semi-conjugacy in the weak sense. Okay. So this is a final of main part. So I think that here is a good point to give a question. But how about Emmanuel?
Yeah. So I have a question.
Okay.
So if you go back to your logistic map plot.
Okay.
Yes, this one. So then where is the can you break down the listening phase and the learning phase and the predicting phase? Like, how do you go about to get this prediction? Like, so you
yeah. Okay. This is okay. This is a graph on predicting phase. So the blue solid line is target dynamics. So this is firstly, in the case of logistic map, we can think the manifold M is R1, so one-dimensional line itself. So we don't think about the observation function phi, or observation function phi is identity on R1. And after that, the blue solid line in the left figure is that the xn or xn after capital T. And the orange dotted line is Rxn. Excuse me, double Rn after n larger after T. This is obtained output by a Reservoir computer. And the orange points on right figure is double Rn and double Rn plus 1. And blue line is, of course, xn plus xt and xt plus 1, or logistic map, graph of the logistic map itself. Does it make sense?
Yes. So have you tried it for like more than higher dimensional maps, like 2D and higher?
Okay. Yeah, that's a good point. And one-dimensional case is a logistic map, and two-dimensional case is an Enon map. And actually, I do a map on torus, but two-dimensional torus, and one-dimensional circle. And some other researchers, many other researchers try to do reservoir computer for the Lorenz system on R3. But maybe for theoretical example, R3 is maybe the biggest case. However, some researcher interested in application of reservoir computing is, of course, try to do apply the reservoir computer method for any other actual time series. And in many numerical experiments suggest that maybe reservoir computer can be used for more and more higher dimensional dynamical system. I mean so deterministic dynamical system. Yes. So I do just a map for one or two dimensional map, but other researchers try to do for three or more and more higher dimensional dynamical system. Yes.
Thank you so much. Yep.
Thank you very much. So can I go to the technical part, or any other question for here? Okay, if some of you have question for main part, please ask me in any timing. Okay, let's move on to the technical part for the latter half of this talk. So the technical part is contained 4 steps. The first step is a theory of listening phase, and the second step is theory of predicting phase. The reason I don't take theory of learning phase step 2 here is that the theory of learning phase is a little complicated and different from the listening and predicting phase theory. So after introducing the listening and predicting phase theory, I will state main theorem in the formal form and give the more precise detail of the sketch of the proof. And finally, if I have a time, I will give a theory of learning phase. Okay, so let's start from the theory of learning phase. So the what we want to do in this theory of learning phase part, what we want to do is that the step 1 in the outline of the proof. Okay, so what we want to do say is there exists a gamma from gamma gamma to lambda. This is a C1 diffeomorphism, and this gamma make the diagram of the lower part commute. This is the aim of this part. So to show that, firstly, I have to define the skew product system from the dynamical system theory. Okay, in such a setting, x and y 0, and f is dynamics on x, and capital F is a dynamical system on x times y to y. And maybe, as you can find, this form is very, very same as the reservoir map, the form of the reservoir map. And in the terminology of the skew product system, we can say that the combination of the target dynamics F, unknown target dynamics F, and the reservoir map can be said as a skew product system with a base step X and fiber space Y. In the Reservoir computing setup, F can be solved as a manifold M, and a fiber Y is a very higher dimensional Euclidean space Rn. Okay. Yes. So the theory of the listening phase can be solved as a skew product system. And one of the most important concept in skew product system theory is a fiber contraction. That is clear from the naming of the fiber contraction. That is the map F is contraction, has a contraction for the with respect to fiber. So formally we can like this. Okay, and in this talk we refer to F has a strong fiber contraction if this kappa, this is a kind of Lipschitz constant, is very, very small. How small this is determined by the proof of the theorem. Okay, but by the way, we call in such a situation we call F is a strongly fiber contracting, and one of the key concepts for saying the existence of gamma is the invariant section. The invariant section is formally defined in some form that same. Sorry. There are different form, essentially same, but different form. But maybe I think most understandable form is this. S is invariant section over x0 if the diagram commute by sigma and F and F. And this S is defined by sigma and projection Y. Okay, and we refer to if the invariant section S exists and CR, we call the S is a CR section. And one of the classical theorem in the skew product system theory is that CR section theorem. So in some good enough setting, there exists only one CR invariant section for the skew product system F and capital F. So by using this, the first part of this main theorem is obtained clearly from the classical theorem, CR section theorem. Okay, the main one of the main theorem in this part is theorem 2.2. In that says that in the setting of the Reservoir computer I introduced before, and if the target dynamics F has a property of diffeomorphic, and the reservoir has a property of C1 strongly fiber contraction, then the system F and F omega has a unique C1 section. This is clear from CR section theorem. And additionally, we suppose the rank condition for the reservoir. And note that this rank condition is satisfied by if this rank condition satisfies if you use the tau equal tangent hyperbolic. Okay, so this is very mild condition for reservoir computation, and if we put this another condition R2, then we can say that S omega, this is a unique C1 section, is an embedding. And because this is embedding, particularly speaking, this is of course injective. Yes, and note that this second part of this theorem 2.2 is a generic property. That is, if one take omega as zero matrices, clearly the embedding is not obtained. But such a ill-conditioned matrices such as zero matrix is not so many in the space of omega. Precisely speaking, generic is of course meaning that the open and dense set. So in the space of matrices, there is open and dense set of omega that makes S omega is an embedding. And after that, theorem 2.3 is more technical, but the most important point is that because S omega is embedding particular injection, there exists a left inverse of S. This gamma is what we want to say ideal output in the step 1. And by defining F tilde gamma, this F tilde gamma S and Fm is C1 conjugate. And the third and fourth part says that the attractor of F tilde gamma, we wrote gamma gamma, is defined, can be defined, is the message of 3 and 4 in this theorem. So, in short, this theorem told that there exists gamma that makes the lower part of the diagram below, the left diagram, and this gamma make this part commute, and this gamma is defined precisely. This is a message of theorem 2.3. Okay, here is a strategy of theorem 2.3, but this is too technical, so I skip this. And this is a numerically obtained attractor gamma gamma for the case of logistic map. As you see, the x coordinate is x itself, and y coordinate is one coordinate of reservoir space Rn, and as you see, this gamma gamma is very smoothly seems very smoothly conjugate to the attractor of logistic map itself. Okay, so the second part of technical part is theory of predicting phase. That is the third part of the algorithm. So to move on to the theory of the predicting phase, what the key concept is topological stability. This is in the sense of Masato Hara in 1978. The topological stability in the strong sense is there, if F and G is in C0 close, there exists H such that close to identity in the sense of C0. This is a condition 2. And Z is a topologically semi-conjugate in the weak sense to F. So that is H is C0X. G is excuse me. Oops. Yes. Excuse me. But I try to say again. If F and Z is C0 close, there exists C0. There exists H close to identity in the sense of C0, and this H is continuous map. Okay, this is the topological stability in the sense of Masato Hara. But the point that is the space of Z, the phase space of Z and F is same, X, in the setting of Masato Hara. So to setting, the different attractor if the dynamics of F and G has a defined attractor gamma G and gamma F, so to generalize it, we make a new definition we call ambient topological stability. Yeah, this is, in short, if F and G and C are close, there exists H close to identity X and the diagram commute. Okay. Okay, and by the way, this is maybe many of you know there is some another concept from dynamical system theory that is called POTP, or shadowing property. That is, oh, excuse me. Yeah, this. We call delta should orbit if the orbit of the orbit of this and this and this is delta close to the true orbit of xj minus 1, xj, and xj plus 1. Excuse me, I try to say again. If xj minus 1, xj plus 1 satisfies the condition that if xj minus 1 is delta close to xj, and if xj is delta close to xj plus 1, blah, 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 then we call this is a should orbit of F. And this should orbit is epsilon trace when if there exists true orbit fj minus 1y, fjy, fj plus y1, blah, 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 is in the epsilon neighborhood of xj minus 1, xj, xj plus 1, blah, blah, blah. In such a situation, I mean, if for all delta should orbit is epsilon traced by true orbit, we say that the system has should orbit tracing property, for short POTP. POTP is a kind of very good condition for dynamical system. And another good condition for dynamical system is positive expansiveness. And importantly, Masato Hara shows that positively expansive and POTP dynamics has a topological stability in the strong sense. So by using this, if we suppose the target dynamics F has a positively expansiveness and POTP, then the ideal autonomous reservoir restricted to its attractor is ambient topological stable. This is just a generalization of the theorem of Masato Hara. Okay. So finally, we can state the main theorem in the formal form. This seems very complicated, but note that this is actually not so complicated message. This has not so complicated message. The red part is important part. Suppose the target dynamics F has good enough conditions such as diffeomorphic and positive expansive and POTP, and the reservoir map F has a good enough condition such as C1 strongly fiber contraction. This is satisfied if we take this omega as very small. This omega has very small spectral radius, and if T1, T2, T3, and R1 is satisfied, then there exists S omega. Moreover, if we take tau as tangent hyperbolic and the R2 is satisfied, then S omega become an embedding for generic omega. This is just same as first main theorem in the previous part. And moreover, if we propose the hypothesis H, that is for actual output, double is close to phi gamma, then the main theorem what we want to say that is F omega is semi-conjugate to F in the weak sense. So in short, we show that in step 1, and we show step 1 and step 3 by using the skew product system theory and Masatoshi Oka's topological stability theory, and we put hypothesis as this step 2 is satisfied. Then, as I told previously, the main theorem, this is obtained. Okay, this is a whole story of the our main theorem. Yes, this is basically same as my explanation, so I skip. Yes, and numerically, the conjugacy map is obtained. This is a logistic map case, and yes, so this main theorem is, of course, the logistic map is not diffeomorphic, and of course, not positive expansive and PODP, but numerically, this theorem seems to be good for logistic map. So yeah, okay. And finally, the remaining part is that when the H or step 2 in the main part, when this H is obtained, is the remaining problem. And the answer is that if we put the another assumption, that is T4, R3, sharp, and star. So I mean, F is ergodic with respect to mu, and by using this mu, F omega and F omega transpose is invertible. And for the tangent hyperbolic or activation function, this is L finite. I have not defined L finite, but there is, yeah, but this is good for the case of tangent hyperbolic. And finally, this star condition is that support is, the mu has a full support on attractor lambda. If put this T4R3 sharp star, the hypothesis H is true in many cases. The the precise meaning of the many case is that probably greater than any other alpha for sufficiently large n and t. And this means for very, very good big reservoir, and if we have very, very many trajectory of the target dynamics, then in many cases, the hypothesis H is true. So for short, if the dynamical system has T1, T2, T3 plus T4, and the reservoir map satisfies R1, R2, R3, and additionally sharp and star satisfied, then the main theorem is true for many cases in the sense of here. There are many points to show this theorem 2.6, but I just to comment that is we use firstly universal approximation theorem that is deeply researched in the area of the machine learning theory, and we also use ergodic theorem in some sense. This is our new proposition. In this sense, we use we use a kind of not so difficult, but a kind of measure theoretic theorem. So by using ergodic theorem and universal approximation theorem, we can show theorem 2.6. So let's conclude this talk. And RC algorithm can be described as a three-step, and the listening step can be understood by using skew product system theory, and the predicting phase theory is made by using topological dynamical system theory. Although I didn't mention the topological stability theorem is firstly made by Rufus Bowen, and after Walters and also Masato Hara do some works on topological stability theory. And the shear section theorem is very traditional from hash or pure. And in the proof technique, we use Hoyt-Innes or Takens's embedding theorem. And I skipped, but in the learning phase, this is a kind of major theoretic dynamical system theory, and we use universal approximation theorem from machine learning theory, and we use Barkov's ergodic theorem for that proof. And so if we use this many dynamical system theoretic concept, we can show the main theorem, that is the reservoir after learning F is semi-conjugate to the F itself in the weak sense. So the remaining problem is that how about non-invertible or more worse dynamics of F? So the weak point of our theorem today is logistic map or tripling map, or of course NO map or Lorenz map cannot be understood just by our theorem, because such Fs don't satisfy the assumption T1, T2, T3, T4. One of the most crucial part is the T1, that is invertibility part. So to blow this theory to non-invertible case is one of the most important generalization. And the second important generalization is that in this theorem, I talk today, is the theory for semi-conjugacy in the weak sense. But what we want to have is a conjugacy, or at least semi-conjugacy, where the condition for saying conjugacy or semi-conjugacy achieved is the second message is that how dynamical system theoretic RC is. This is a very important point from the viewpoint of the mathematics, especially the dynamical system theory. Okay, this is the last slide. So thank you for your attention.
Okay, thank you very much. That was a wonderful talk. It's oh, and if you will, I'll click the clap emoji there, of course. For that was a very interesting talk, and yeah, I like that last point. It's very interesting to see how much theory is actually behind reservoir computing, when it can otherwise just feel like unexplainable machine learning sort of thing, but it's not. That's really important. So yes, I think we have some time for some questions. If anybody had one, please feel free to ask.
Yeah, I have a question.
Sure, Mohammed, please.
Yeah, thank you for the talk. So I'm a bit familiar with the sort of the skew product flow approach to non-autonomous dynamical systems, but I'm not. How does, like, for example, the concept of pullback attractor relate to a CR section? Are they the same?
Sorry, I couldn't hardware, but sorry, and not for non-autonomous system. Pullback attractor. Sorry, could you tell me again? Sorry.
Yeah. So I was saying, can you hear me?
Yes.
So I was saying, how does the concept of a CR section relate to a pullback attractor? Are they the same?
That's very good point. Thank you very much for your question. Yes, as you say, maybe your point is good point. And In fact, I believe that for make generalization to non-invertible case, I mentioned here, is obtained by using, okay, using a correspondence of invariant or C1 section S omega to the non-invertible case. The key point, the difficulty is that shear section theorem is just hold for the case of f is diffeomorphic. But as maybe you mentioned, for invertible case, we believe that the correspondence of S omega is a kind of pullback attractor or inverse limit or something like that. So yeah, maybe such a non-autonomous concept can be must be used in the generalization of our theorem.
Mm-hmm. Thank you. Thank you.
Thank you very much.
Any other questions? Oh, I think I said, go ahead, Emmanuel.
Yeah, I got one last question. So basically, you mentioned that long-term prediction is impossible. Is that correct? Long-term prediction is impossible.
Actually,
long-term
what?
prediction
What prediction?
using the reservoir computing is not possible. You probably mentioned that in the beginning. Was that correct statement? Long-term prediction, like
long-term prediction.
Like if you have to go very far ahead in your time series, and you're trying to fit like this, trying to observe and learn these dynamics for a very long time, is that possible using reservoir computing?
Long-term prediction. So you mean this long-term prediction?
Yeah, like if you have to go very far.
Okay. Yeah. Maybe long-term prediction cannot be done by using any tool because of the chaoticity. However, the problem is the problem setting. So if you have how should I say? If you have if you can use data after learning, so make learning for example, in this case, that prediction for 10 step or so is good enough. So if you can do relearning, so 10 step and 10 step and 10 step, 10 step, then such a long-term prediction can be done. But in my problem setting, in our problem setting, if we use very large and very long trajectory, if we use very large reservoir and very large trajectory, or using some other putting some other the long-term prediction cannot be done. This is not a problem of reservoir computer, but the problem of the chaoticity, I think. Does it make sense?
No, thank you. Thank you.
Yeah, thank you.
Sorry, one last question from me. Is there? Do you have like a paper that someone can refer to for this talk?
Unfortunately, no today. This is because my paper is just submitted and on the actually, I'm now writing a letter to referee, but we shall upload the final draft of this paper after the acceptance. And moreover, my PhD thesis will be uploaded on the repository of Kyoto University, where I get PhD degree after the acceptance. So maybe in this year, there are some way to access to the work of us. And for now, most good reference is the thesis of Alan Hart. Do you know Alan Hart? In the do you know? Okay. Yeah. Paper of Alan Hart that can be obtained on archive. I think that the Alan Hart thesis is the best choice for now. But of course, this is just our work. So please wait for the acceptance of this paper. Yeah.
Thank you.
Thank you very much.
I had a quick question, just out of curiosity. Is there any system where the conditions of your theorem do not hold, where this breaks down? Is there a sort of an obvious counterexample, for some sort of non-nice dynamical system where you don't achieve this conjugacy?
Sorry, no noisy. Excuse me.
Is there an example of a dynamical system where the theorem does not apply?
Okay. That's of course good point, but for now, no. That is because the theoretical example which we can compute is how should I say? There are very few examples. For very few F, the experiment is done for now. So logistic map case, NO map case, Lorenz equations case, and the tripling map case, and hyperbolic total automorphism case, and such a case, and most small system case, for such a case, Reservoir computer work well, but yes. So for short, there is no clear example for the counter example, but in fact, I believe there should be some example, because our theorem for now has very crucial, very strong assumption for target dynamics. So I believe some there are some map which is not good for reservoir computing, but for now I couldn't find such a system. If you have some suggestion, please.
Oh yeah, no, I don't off the top of my head. I just ask because it always helps me to understand a theorem's power by knowing where it fails, or where the assumptions aren't satisfied. But yeah, it's very interesting.
Yeah. So the another point is that this theory is too strong. Another possibility is that this theorem is too strong. So from the theoretical viewpoint, we have to try to change this T1, T2, T3. So in particular, T2 and T3 is one of the strongest parts. If F has T2 and T3, F is close to uniformly hyperbolic. And such a system is not so generic in the space of all dynamical systems. So yeah, there are many problems for this theorem. Yeah, but this is the first case, and from judging from the numerical experiment, this theorem must be made stronger. Yes, I think.
Sure.
Yeah, thank you very much. Yeah.
Okay. Any other questions? Okay. Well, thank you, Masato, especially for giving a talk so early your time. We really appreciate it. It was a wonderful talk. And if there's no more questions, then I guess we'll just see y'all next time.